Topic 2 is all about quadratic functions. In this topic, we'll look at different ways to write a quadratic function, different ways to graph it, and unique ways to solve. In 2.1, we'll look at vertex form. This is the type of quadratic function that's the most familiar to us. We'll identify key features and write equations. Now remember, a quadratic function is anything of the form f of x equals x squared. And we talked about ways to describe the transformation from this parent function. We have two examples on the right. Describe the transformations to the parent function f of x equals x squared. Then graph the function. In the first example, we have g of x equals negative times x plus 2 squared. The negative is going to reflect over the x-axis, which means the arrows will point down. That's a V right there. And the x plus 2 on the inside moves the vertex 2 units to the left. So we know we're going to go left 2. Notice there's no up or down, so as we look at the sketch of this graph, if we count 2 units to the left, like so, our axis of symmetry would be at x equals negative 2. And since there's no stretching, that's an arrow right there, sorry. Since there's no stretching or compressing, we would go 1 to the right, and instead of up 1, we'll count down 1. Go 1 to the left and down 1. Go 2 to the right, and we'll go down 4. 2 to the left, down 4, and so on. Modeling the parent function table. And then this opens upside down. The next graph, we have a couple of things happening here. Notice it's h of x equals 2 times x minus 1 squared plus 2. Now that first 2 will cause a vertical stretch by a factor of 2. The x minus 1 on the inside will move the graph right 1. That would be the vertex. And then the 2 on the outside will move the vertex up 2 units. Normally that vertex, that turning point is at 0, 0. We'll now go 1 to the right and up 2. Oopsie, here we get that in. Oh, wow. Try that again. 1 to the right and up 2. That axis of symmetry goes right through the center. And because it stretches by 2, from the vertex, we'll go 1 to the right and up 2, 1 to the left and up 2. Go 2 to the right, instead of up 4, we'll go all the way up to 8, which will put us at the top of our graph because we're doubling our normal outputs. And this parabola, or this graph, would open up. So speaking of the word parabola, you see that word over on the right-hand side. The parabola is the name of the shape for a quadratic function. So both of those kind of curved shapes are called parabolas. Every time we talked about transformations from the parent function, we were actually working with what's called the vertex form for a quadratic function. And that models y equals a times x minus h squared plus k. Anything that has a parenthesis being squared and then things possibly being added or subtracted after is the transformation of the parent function. Now the key features you're going to want to find are the vertex, and we've done this before. This is just kind of a new way to go about it. Remember the vertex for the inside, we always go in the opposite direction for x minus h, so that would just be positive h. And anything on the outside is the same sign. So we need to know that vertex. We also draw in our axis of symmetry. And it's always the same as the h coordinate from the vertex. So it's going to be x equals whatever that number is. And that's that dotted line we draw in. Usually we look for the y-intercept, and we plug in, hopefully you guys can read what that is, sorry. We plug in the y-intercept. That means we let x equal 0 and simplify. So instead of describing using transformations, we can kind of follow this key information set to give us our results. It says, what are the key features for the quadratic function f of x equals 2 times x minus 3 squared plus 4? Now, instead of describing the transformation in words, we'll just use these key pieces of information on the left. The first thing we want to find is the vertex. And the vertex is found from translating 0, 0. It does say x minus 3 in parentheses. That means the vertex would translate 3 units to the right. And then plus 4 after means it would go up 4. With that information, our axis of symmetry is going to be the equation for that vertical dotted line. And that always matches the x-coordinate, so x equals 3. Let's see our y-intercept here. It's where it crosses the y-axis. So now we have to do a little bit of work. If we want to find the y-axis, we're going to plug in 0 for x. We get 0 minus 3 squared plus 4. Well, 0 minus 3 is negative 3, but negative 3 squared is 9. 2 times 9 is 18, and 18 plus 4 is 22. So the y-intercept is 0, 22. But that's pretty big. That really won't give us a lot of useful information. So let's see what we can do using our transformation, describing that a value at the front. Our vertex is 3, 4. Let's go ahead and plot that. Our axis of symmetry, I'll draw that in using a different color. There's our axis of symmetry. So now instead of trying to plot the y-intercept because it's too big, that number 2 that's out in front is a stretch vertically. So I'm going to say stretches by 2, which means we'll count 1 to the right and up 2 like we did on the example before. And then 1 to the left and up 2. If we go 2 to the right, we have to go up 8, so that's going to be too far on our graph. I think we have enough to just sketch our curve through those points. And there is your parabola for that vertex form. And now look at what we get to deal with. Domain and range. Wow, we thought we were done with those. Not even close. Remember, domain is the set of all possible inputs for our function. And in this case, we can plug in anything we want for x and square it. Notice the arrows on the left side and right side technically both point up, but they also go left and right forever. That would make our domain anything we want from negative infinity to positive infinity. Our range, we always read bottom to top. Well, there's no arrow for the bottom of that parabola. It has a minimum value, a low point, and that's at positive 4. We put a bracket there because it can equal positive 4. And because both arrows point up towards positive infinity, we'll end our range with positive infinity. When asked to write the equation of a quadratic function, we no longer have to worry about trying to guess maybe if it's being stretched or compressed. We've got a set of steps to follow that will allow us to write the equation of a quadratic function in vertex form. The first thing you want to do is plug in h and k to the general formula for a quadratic function in vertex form. Y equals a times x minus h squared plus k. That'll be step 1. Step 2, you want to calculate what that a value is. So we need to know, is it going to stretch or compress? If it opens upside down, that means a would be negative, that sort of thing. To do that, what you'll do is you'll pick another point to plug in for x and y. And then that will allow you to solve for your a value. Let's try our example on the right. Write the equation of the quadratic function. Notice it opens upside down. The arrows both point towards negative infinity. That means the vertex is up here at the top, there's your h, and there's your k value. Oops, k, there we go. If we start with our formula for vertex form, y equals a times x minus h squared plus k. If h is -2, that means on the inside, if we plug in -2, that becomes x plus 2 squared. We always switch the sign for the x value. And then k is +3, so we add 3. So now to calculate our a value, notice on the graph there's another point that we can substitute in for x and y. The y value is -1 when the x value is 0. Leaving everything else unchanged, now our only variable is the a value. Now we have to be careful on order of operations here, so I'm just going to say watch your steps. And here's what often happens. 0 plus 2 on the inside is 2, and 2 squared is 4. We get -1 equals a times 4 plus 3. But if we think order of operations in like terms, a times 4 is the same as 4a. So you don't want to combine the 4 and the 3. They're not like terms because 4 is with the variable. What we will do, though, is move 3 to the other side. -1 minus 3 is -4, equals 4 times a. Divide both sides by 4, and the lead coefficient is -1, which makes sense because the quadratic function opens upside down. Last but not least, finish your equation. To do that, we just plug in a up where we did in step 1. So we have y equals a, which is -1. The 1 is optional, but keep the negative part. And then keep x plus 2 squared plus 3. That's the equation of your quadratic function for that graph in vertex form. We'll finish the rest of our notes tomorrow in class.